Well, welcome to our little chat about trig derivatives, and I'm going to lead off kind of by spoiling the surprise. I'm not going to go through the complete definition of the proof here of the oh, yeah, I guess I said a bad word, didn't I? I said the P word. I'm so sorry. Um, you know, we'll just pretend that that doesn't exist right now, I suppose. Uh, maybe I have to edit the rating on this video now that I've said bad words. So the derivative of the sine function is going to be the cosine function, and the derivative of the cosine is the opposite of the sine function. And those two things you can get through our special trig limits. And if you watch the Khan Academy video that's linked on our page, then you know that that's what it works out to be. I'm just going to kind of ruin the surprise there. If you want to watch the whole how the proof comes together, you certainly can. But derivative of the sine is cosine. Derivative of the cosine is negative sine. So what does that do for us with the tangent function? How can we get the derivative of the tangent function? Well, if you remember, a lot of times we can rewrite our trig functions in other ways. Namely, the tangent can be written as sine of x over cosine of x. Now, if I want to find the derivative of that, I am stuck using the dreaded quotient rule. Another sound effect there. Okay, now the quotient rule at this point shouldn't strike a whole lot of fear into your heart, but here we go anyway. So if I want to find the derivative of the tangent function written as sine over cosine, then it's going to be low times the derivative of the high function. Okay, well, the high function is sine x, and we've just established its derivative is cosine x. And then it's minus high function times the derivative of the low function, which is cosine. Derivative of cosine is negative sine of x. And this is going to be all over low squared cosine squared of x. All right, now this is going to come together real fast when you see that this is cosine squared of x. And then when you distribute the negative and do a little cleanup on aisle 1, you've got plus sine squared of x all over cosine squared of x. Now, at this point, your trig identities are going to tell you something very interesting, that this numerator is going to evaluate to 1. And that's going to give us 1 over cosine squared. And for our bonus prize, we know that the reciprocal of the cosine function is, of course, secant. So the derivative of tangent squared is indeed secant squared, and that is something that is helpful to know. So we've got the derivative of the sine, the cosine, and the tangent. We've got all that down already. Isn't that fantastic? Okay, so before we get to what's up above, I want to go ahead and fill in the rest of this table here. We know that the derivative of the sine is the cosine, and the derivative of the cosine is the opposite of the sine. We also know that the derivative of tangent is secant squared of x. We know that from the previous panel there. And now we've got to come up with derivatives of the rest. Well, since these are all functions that rely on our relationships between sine and cosine, we can definitely put ourselves in a position where we know what these functions are by using quotient rules and so forth. But I'm going to spare us the pain, and I'm going to say that the derivative of the cotangent is negative cosecant squared of x. The derivative of secant works out to be secant of x times the tangent of x. And the derivative of the cosecant is negative cosecant of x cotangent of x. And that's going to be our derivative functions. Now, of all the things in this unit that you really want to commit to memory, these would be it. You really want to get these under your belt as quick as you can, because knowing these things is just going to speed up a lot of the problems that we will run into in the course of time. So backing up to the examples at the top, if I want to find the derivative of x minus tan x, well, the derivative of x is just 1, and then it's 1 minus secant squared of x. Now, if you wanted to push your luck and try to do something extra with like a trig identity there, I don't see the reason why you really should, because it kind of looks like a Pythagorean identity. Let's just stop right there for the moment so we're not overcomplicating this. Okay. Now, in this second one, I've got to use the product rule because I've got x times the secant of x. So it's like that's my u and that's my v. So if I go to do the derivative, it's going to be u prime, which is 1, times v, secant of x, plus u, which is x, and then v prime, which is going to be secant of x, tangent of x. And honestly, there really isn't any purpose to doing anything else with this, so I'm just going to stop the madness right here and call that good. You know my rule on simplifying by now. If you have a purpose for simplifying, then by all means go for it. But if you don't have a purpose for simplifying or carrying it any further, then there is really no need to risk any sort of unnecessary or unforced error, I guess. So that's something to think about for sure. Once again, it looks like we have the curse of the revenge of the quotient rule. Okay, so here's our u, here's our v, our upper, our lower, our high and our low, whatever you want to call it. Okay, so the derivative is low d high, which is cosine of x, minus the high function, sine of x, times the derivative of the low function. Okay, so the derivative of the low function, that's going to be negative sine x for that, and then that 2 is a constant, so it go bye-bye. Everybody say goodbye to the 2. Goodbye, 2. Thanks for playing. And then down below, this is going to be the quantity cosine x minus 2 raised to the second power. Okay, little cleanup in order here. So we've got cosine squared of x minus 2 cosines of x, and then we've got a sine plus sine squared of x, and this is all over cosine x minus 2 raised to the second power. And once again, we quickly notice that cosine squared and sine squared, those are going to add to 1. So I have 1 minus 2 cosines of x, and then cosine x minus 2 raised to the second power downstairs. I don't see the purpose or the necessity to cancel anything or even the legality of canceling anything. So I think we're just going to go ahead and leave it right there. Okay, now here's the interesting situation where, as you know, because of our ability to rewrite questions in different forms, well, we can differentiate both forms of this because, as it turns out, 1 minus cosine over sine, if you simplify it, it's the same thing as cosecant minus cotangent. Okay, now I'm going to spare us the pain on this one because we all know this is going to require, yep, you got it, the quotient rule one more time. And, you know, I'm sure as many times as we've used the quotient rule, you probably are reaching the point where you're saying, if I have to use that quotient rule one more time, it's just going to make me say... Okay, so we're going to try to avoid using the quotient rule here, because if they work out to be the same thing, then why mess with something more complicated when we can do something a little bit easier? The derivative of cosecant is negative cosecant of x, cotangent of x. And the derivative of cotangent is negative cosecant squared of x. So doing a little cleanup, I'm going to have negative cosecant of x, cotangent of x, plus cosecant squared of x. You could do that in either order, just so long as your signs are correct. And that's what it's going to work out to be. You know, again, could you make things easier on yourself? Yeah, you probably could, but, you know, anytime we can avoid using the quotient rule, that will cause everybody to go... Okay, so that's going to be the essence of this particular example right here. I'm not going to worry about doing the other part. If you really want to do the quotient rule, please be my guest. Now, because of trig identities, a derivative of a trig function can take on many forms, and much of the work obtaining a simplified form of a derivative occurs after differentiating. So, two characteristics of a simplified form are the absence of negative exponents, and I know that really doesn't necessarily apply here, but sometimes it will with polynomials, as we've discovered, and the combining of like terms. Okay, and we sometimes write as one fraction just to try to simplify things. Sometimes, I mean, not always. Okay, so in this situation, I have to take a step back before I differentiate. As the old look before you leap idea. A lot of students just want to go dive right in, and barging right in is a strategy. I didn't say it was a good one, but it is a strategy. And in this case, I notice I have x squared times sine x. Times. So that's a signal that I need to use the product rule because we are multiplying these two functions together. Okay, so if I'm using the product rule, then here's my u and here's my v, and let's see if we can get the derivative by doing u prime, which is 2x, times v sine x, plus u, x squared, times v prime, which is cosine of x. And really, there's no other simplification or anything else that we can do here that makes any kind of sense. Now, if we were trying to find some more information out, I might consider factoring out an x, but I really don't see the purpose behind it. So I'm just going to put a box around it and walk away. Okay, let's investigate this one. Cosine x over 1 minus sine x. Aha. Well, now it's time to use the, And the reason why is because we are dividing these two functions. So u is equal to cosine x over 1 minus sine x. Rewriting it sometimes gives us an opportunity to tackle it from a different perspective. Okay. So let's see what we can do here with the derivative. Let's go with good old Cab Calloway here. Low is 1 minus sine x, and derivative of that is negative sine up top. And then high function cosine x, and the derivative of the low function, well, that constant goes away, and the derivative of sine is cosine, but I've got that minus in front, so negative cosine of x, and then this is going to be all over 1 minus sine x raised to the second power. Okay, how about a little cleanup? It looks like it's going to be negative sine x plus sine squared x plus cosine squared x when I simplify the numerator. And, lo and behold, that turns out to be 1, as we all know from our Pythagorean identities. So this really shakes out to be 1 minus sine x over 1 minus sine x as a quantity raised to the second power. Okay, now you can cancel something. Now you can definitely cancel something, and it's legal to do so. So we're going to be really happy about that one, because that cancels that and cancels the power of that. Friends, don't forget that when you cancel something up top, you got to leave behind a 1. Seen that way too many times. So there you go, 1 over 1 minus sine x. All right, now trig functions are really good in physics situations. Calculus is really good in physics situations, so we're going to combine the two very briefly here. And the motion of a weight bobbing up and down on the end of a spring is an example of what we call simple harmonic motion. I think I've got a sound effect for this too. How appropriate is that? Okay, so what we can do is we can model this because if it bounces up and down and up and down and up and down, a sine wave as a graph does the same thing. Now, granted, it kind of goes across a length of 2 pi whenever it does a complete wave, but this is something to think about for sure. So a weight hanging from a spring bobs up and down with a position function of 3 sine t. And we want to know what its velocity and acceleration are. Okay, velocity is going to be the derivative. And acceleration, as we found out, is the second derivative. So this should be super easy to do. Okay, the derivative of this particular function, s, is going to be s prime of t is going to be 3 cosine t. That was pretty easy to do because it's just constant multiple rule there. And the second derivative, the acceleration function, will be negative 3 sine t. Now you can see that this is going to bounce back and forth between sines and cosines and positive and negative if we keep going multiple derivatives beyond just the two. Went a little too fast there, so let's stop here. A jerk is a sudden change in acceleration. Okay? And when a ride or a car or bus is jerky, it's not the accelerations involved are necessarily large, but the changes in them are abrupt. And I encourage you not to use this in any other context. There will be no name calling in this class whatsoever. Okay, I'm not going to call you names. Don't call me names, even though I'm sure you're tempted from time to time. Jerk is the derivative of acceleration. So if the body's position at time t is s of t, then the jerk, let's change that to an s if we can. The jerk is going to be the derivative of acceleration. Well, the acceleration is the second derivative, so this must mean the third derivative of acceleration, or of position rather, sometimes known as d cubed s over dt cubed, with that Leibniz notation. All right, so now you dirty, rotten third derivative of position. Okay. Now, right here, this is the acceleration that we're being given. Keep that in mind. This is the acceleration of a constant, body in motion that's in free fall here. So if I wanted to find the derivative of that, then the derivative of that is just going to be 0 because it's a constant number. So anything under free fall is probably not going to have jerk at all to speak of because there are no sudden changes in acceleration. It's going to very smoothly and calmly accelerate towards Earth until we hear a splat. Okay, so now let's find the function for jerk of this simple harmonic motion. And the first derivative, s prime of t, sometimes known as v of t, that's going to be, in this case, negative 5 sine t. Then the second derivative, sometimes known as a of t, is going to be negative 5 cosine of t. And then the third derivative, I don't really have anything clever for the notation there, is going to be 5 sine t. And I mentioned this on the other panel. You can see how the functions are going to bounce back and forth between sine and cosine as we go through this. All right, let's do a second derivative of just a trig function. And this is going to look kind of, not going to be too bad. I mean, the first derivative is going to be secant x tangent x. All right, that seems relatively harmless. I mean, nothing too serious there. But if I want the second derivative, I am going to have to use the product rule. And the reason I'm going to have to use the product rule is because I'm multiplying two functions together. So this is going to be my u, and that's going to be my v. And let's see what shakes out when we do this u prime v plus uv prime business. So u prime will be secant x tangent x, times v, which is tangent x. And then u is going to be secant of x. And then v prime should be secant squared of x. Okay, a little bit of cleanup here will give us secant of x, tangent squared of x, and then 3 powers of the secant in that other term. That wasn't too horrible at all. I think you'd agree that was pretty calm and tame. This one, however, well, let's look at this and find out what happens. We got a lot of theta, so we're going to take derivative with respect to theta instead of x. And right off the bat, we notice that it's going to be... Okay, so now we know that it's product rule. Let's go ahead and dive in here. And u prime, which is 1, times v, plus u times v prime. Okay. And now we've got to start thinking about the second derivative. Okay, well, this part is not going to be so bad. This part, on the other hand, is going to be disgusting. And we say that because we've got tangent of theta plus theta times secant of theta times another secant of theta. So this is going to necessitate the 3 product rule version. And that's going to be, gross. Okay, well, sooner the better. Let's just dive in and see what happens here. So the derivative of tangent is secant squared of theta. Now for this part, I have to differentiate these things one at a time and multiply them by the other 2. So if I differentiate this theta, it's just going to be 1 times secant squared, or 1 times secant. So that's going to be secant squared of theta. Okay, good to know. Now I differentiate the 1 in the middle, which is going to be secant tangent. So in order here from left to right, this is going to be theta times secant theta tangent theta times secant of theta. Okay, now for the third part where I differentiate this secant. So it's going to be theta, secant, and then the derivative of this guy right here. So that's going to look like theta, secant of theta, and then secant theta, tangent theta. Holy moly, I'm running out of room. Better start cleaning this up. Okay, so I'm going to notice that these two can get combined right away into 2 secant squared of theta. And then it looks like I've got a couple of like terms because it seems like everything there is really the same thing. I've got thetas, I've got 2 secants, and I've got a tangent as part of the picture as well. So I think it's going to be 2 secant squared of theta, tangent of theta. All right, so that cleaned up very nicely, but it kind of opens the door to an interesting question. I almost wonder if there's a faster way to deal with this part of it than this, and the answer is yes. And I'm going to keep you in suspense for the next lesson so you can find out what it is. I have to keep you coming back for more. And I had to squeeze in one more booing. That's it for this lesson.